continuing along the discussion of the physical responses of the bay and to the water, the physical parameters of the water, Bob Wilson is going to speak now. Bob's also an associate professor here at SOMAS and was involved with the special focus area project I mentioned earlier that he and Charlie had worked on back in 2004 and 2006. So he'll be talking about the residence time and surge, and also, like Charlie's information on the salinity and the temperature, the residence times can be particularly important for some of the biological resources, especially, for example, the shellfish. So with that, Bob.
Thank you, Cornelia. So I wanted to talk about a few practical results derived from the observations that Charlie talked about. But first, I wanted to just review a few things that were revealed by the old modeling that Charlie and I did back in 2006, 2007. The motivation for that project was really to look at the competing interests of the effects of a breach on flooding and storm surge versus the effects of a breach on possible water quality improvements. And this first picture, again, this breach is not really relevant to the breach we're looking at today. It had a cross-sectional area that was approximately 5 times that of the present-day breach. The area of the breach is indicated by the arrow, but this picture shows, for that old breach, changes in the M2 tide range produced by this 3-dimensional model simulation that we did, FBCOM. It's a 3-dimensional finite volume model. It had like 10 layers, very high resolution in space. This picture shows the change in the M2 tide range produced by that relatively large breach at Old Inlet. And what we see, this scale goes from about 0 to 0.4 meters. So it's quite a large change, and this is the change that we see, maximum change in Bellport Bay, but we also see change further to the west in the interior of Great South Bay and further west still. So that old breach did produce a very substantial change in M2 tide range. And that large breach similarly produced a very large change in salinity. This salinity scale goes from 0 to 5 PSU, and what we see is a remarkably large change in the salinity in Bellport Bay up to 5 PSU, which is really consistent with the salinity change that we see today. So the tide range that we saw was extreme, not consistent with what we see today, but the salinity changes are comparable. And very importantly, we ran some wind force simulations to look at storm surge and the change in surge. Most of the simulations we ran were typical northeasters, which means we have winds which are essentially coast parallel, blowing towards the west. And what we see as far as change in response, change in the non-tidal sea level response under northeasters for typical northeast winds is a very large change in surge response in Bellport Bay and further to the west. And what is happening here with this large breach, the typical set down that you see under northeast winds vanishes. So Bellport Bay no longer sets down. You get coastal forcing, which fills Bellport Bay, and then you actually get an enhanced surge. So the coastal forcing versus local setup forcing is still in evidence here, but the local forcing is masked by this large breach, which allows infilling of coastal water under this northeast wind. Is that clear? So there was a fairly substantial change in storm surge response for this very large breach. A couple of conclusions from this older simulation. It did imply significant changes in tide range, surge response, and salinity, primarily in Belfort Bay, but further west as well. These are useful results, but I think Charlie would agree we struggled to represent the breach morphology and the breach geometry. And we found that the response of salinity and surge and tide range was very sensitive to the area. And I think it was a crude attempt. We just changed primarily the area in the inlet. Classical hydraulic theory, such as that by Krogan, 1967, emphasizes that water level response inside the lagoon to coastal forcing, for example, depends in a more complex way on the morphology. It depends on what's called the repletion coefficient, which involves the inlet length, the cross-sectional area, and the hydraulic radius of the inlet. So it's not just the cross-sectional area, it's a bit more complicated. And if you looked at some of Charlie's recent photographs, you can see that it's quite a challenge to represent this complicated flood delta and this inlet in terms of a simple hydraulic situation with a prismatic channel. Anyway, classical hydraulic theory is useful, but it emphasizes it depends on the length, the cross-sectional area, and the hydraulic radius of the inlet. Okay. But again, back to some practical results derived from observations. These are results derived from work by Christine Gurdon and Tricia Clive, who were students at SOMAS, looking at some effects of the new breach on residence time in eastern and central Great South Bay. These estimates are based on a simple salt balance model for a basin and an embayment from Fisher in 1979. Basically, if you have a segment of the lagoon with fresh water coming into it, there's ocean water circulating through that, you can derive a simple salt balance and derive from that salt balance the circulating flow of ocean water through the compartment of the basin. And the parameters are the circulating flow of ocean water, pure ocean water, which is about 31.5 TSU, the salinity of the ocean water, the total fresh water into the compartment of the lagoon, and in our case, these freshwater estimates were taken from our model, which has surface water inflow to the segment of the lagoon, as well as some groundwater inflow. And it depends on the mean salinity of the embayment section and the volume of the segment. And you can set up a very simple salt balance to derive the volume flux of the circulating ocean water, and you can estimate then the residence time of that compartment just by dividing the volume by the circulating flux of ocean water. And Christine and Tricia used this relationship to look at the changes in estimated residence time of different compartments of the lagoon going from Belfort Bay further to the west. And the results are quite interesting. These are estimated mean salinity changes derived from the instruments that Charlie emphasized. In Belfort, for example, for the period indicated here, the pre-Sandy salinity was 23.9. A post-Sandy mean salinity for the period of record they used was nearly 29 TSU. Further to the west at Blue Point, we go from 25.3 to 26.6. Further to the west, let's go to Islip, 26.5 to 27.03. So the salinity change attenuates as you go to the west. The major salinity, the largest salinity change is in Belfort Bay, obviously. And what they found for different compartments containing these gauges was that the pre-Sandy residence time was about 25 days. Post-Sandy is down to 10 days. This is probably a slight overestimate. It's probably smaller than that. But anyway, it goes from 25 days, and the compartments represented primarily by Belport Bay, down to 10 days. As you go further west, there's still a reduction in residence time of the compartments that they considered. The central compartment containing Blue Point went from 85 days down to 68 days. And as you go further west, compartments containing Iceland went from 81 days down to 74 days. Major changes in the residence time of Belport Bay, certainly. And it's interesting to note that the pre-Sandy residence time that they estimated in Belport Bay is very consistent with high-resolution particle tracking simulations done by another graduate student using 3D models. And just to repeat, the results emphasize a marked reduction in residence time in Belport Bay from like 25 days down to 10 days. The residence time changes attenuate as you go further to the west. And very importantly, the observations that Charlie discussed afford some opportunity to look at changes in the effects of the new breach on storm surge response. And I wanted to emphasize that the results I was going to show are based on a very limited a piece of water level data at Smith Point and wind data from the central buoy for January 2012 and January 2013, pre and post breach. And this problem certainly warrants further investigation. So these are very limited data. And I should mention, in my attempt to look at surge, I low-pass filtered the data, so running roughly a 24-hour filter through the data to remove the tide to define the surge. That's not the best way to do it. You really should detide the data. That leaves more short-period variability in the surge record. But these are low-pass filters, so this is a preliminary attempt. What I wanted to discuss, similar to some of the things that Charlie showed, was the correlation between surge and wind from different directions. And that provides important insight into the relative importance of coastal forcing, produced primarily by longshore winds, and local setup forcing, and the dependence on wind direction. And secondly, I wanted to comment on the response function between wind and water level, which tells you what kind of surge change you get for a given wind, what kind of surge height you get for a given wind forcing. So this is the response function. And I wanted to look at that as a function of wind direction. So first, some simple results for January 2012 and January 2013 at Smith Point. And pictured here are some pieces of the data. The top figure is the low-pass filtered water level. The range goes from minus 0.2 to 0.8 meters. So there was a bit of a extratropical cyclone of northeaster in this area. On 1/12, this is January 2012. These are the wind components. Blue is east and red is north. These have been filtered. This is a picture of water level January 2013. Same scale. This is a different scale, minus 0.2 to 0.5 meters. And the lower picture is again the wind component. These are unfiltered, and I should have presented a picture for 2012 of unfiltered. But these are the unfiltered east and north components, blue and red. So these are some interesting correlations between surge and wind, and they're similar to the figures that Charlie showed. The top one is for January 2012, and what's drawn here is, on the horizontal axis, is wind direction. So for, say, 50 degrees, this means a wind blowing towards 50, and contoured is the correlation from minus 0.8 to 0.8. And what we see here in the top picture is the relationship between wind and water level. This is low pass, essentially the surge, is highly correlated in a negative sense with a lag of about 20 hours. This is lag for a wind blowing towards about 105 degrees. So the coast direction is about 75 degrees. And this shows that for wind blowing at approximately 110 degrees, you get a very strong negative correlation. This is primarily coastal forcing. If you blow towards the east, you get offshore transport of water, coastal sea level drops, and it drives a reduction in sea level in the interior. Similarly, wind blowing from the other direction towards about 300 degrees, coastal sea level goes up, and you get a marked increase in the interior sea level. Interesting here, this is lag, so this is about 20 hours where the peak is. As you go towards shorter lag, you see that the correlation becomes stronger for cross-shore winds. So this indicates that it's not just along shore, along lagoon winds that are driving the sea level fluctuation. Cross-shore winds at short lags between wind and water level have a significant influence. So this is 2012, and 2013 we see basically the same type of response. At long period coastal forcing, as you go to shorter lags, you get some cross-shore wind effects. So it's not quite as simple as a long lagoon, a long shore wind forcing. There was an earlier paper back in the 80s by another student who's now professor at the University of Delaware, Ho-Chin Wong, who had a very significant field experiment looking at water level throughout the lagoon. His conclusions were that longshore winds were the dominant agent forcing sea level variability in this lagoon, and it was mainly coastal forcing. He looked really hard at a long channel setup and said that was of secondary importance. So his results emphasized coastal forcing. You blow towards 75 degrees, offshore equine transport, coastal sea level drops. Blow the opposite direction, coastal sea level rises, and the lagoon fills. And so these analyses at Smith Point, 2012 and 2013 in January, are not inconsistent with that, but they highlight that cross-shore winds at short period lags are also important.
How does it want to get in and out of the bay?
Well, it comes in through Fire Island. Pre-Sandy, 2012, comes in through Fire Island, and then it comes in through Mauritius.
2 or 3 hours.
Well, no, this is 20 hours here. 20 hours. Well, it's probably inertial period, 18 hours. Explaining the shorter period variability is a little bit more complicated. This is a very interesting picture. Top frame for January 2012, the bottom frame for 2013. And in this picture, I tried to compute the gain, which is the gain, which describes the response of water level, surge water level, to given wind forcing as a function of wind stress. And let's look at 2013 with the inlet, what I see is, first let's look at the scale. This is meters of surge per meter per second of wind. This is for different wind directions. And what I see is, at longer periods, I get a very large response for winds blowing almost in the cross shore. So this is like 120, 125 degrees. And that's stronger than it was in 2012. The color bars on these two figures are the same. Again, this is gain, which is surge amplitude versus wind as a function of direction. I think interestingly, for 2013, I do see some elevation in the gain. That is, for these limited data, the surge response at Smith Point in the far eastern Great South Bay is a bit stronger. And so this certainly warrants more analysis, I think, using longer records. But it also emphasizes that I get a relatively strong response for cross-shore winds. But just to reemphasize, color bar is the same. The gain or the surge response at Smith Point to a given wind speed is higher, a bit higher in January 2013. So it warrants looking longer records in the 2014 and comparing that with more extensive data in 2012. So even though tide range exhibits some phase advancement but virtually no significant amplitude change for the M2, there is some slight increased response of the low frequency, the surge in the interior in the eastern Great South Bay to winds, and including cross-shore winds. A couple of concluding comments here. The correlations figure shows both for January 2012, 2013, correlation at long time lags are maximum for longshore winds. And at Smith Point, it appears to be primarily coastal forcing. For both January 2012 and January 2013 correlations at short time lags, there's a maximum correlation at short time lags between wind and water level for nearly cross-shore winds. So the cross-shore winds deserve more attention. You expect cross-shore winds to become important for fast-moving storms, for example. This 2012-2013, the surge representatives from extratropical cyclones, slow-moving, low-pressure systems. The response function amplitude has similar magnitude for January 2012 and 2013, but it is somewhat slightly higher in 2013. Response function amplitude points to the importance of cross-shore winds in the interior response. So the inlet may have had some effect under its present, under the cross-section that existed in January 2013 on increasing the surge response in the interior. So, any questions?
Yes.
Yes. Those surge plots are based on measurement at one specific location, or it's an average of?
That's one location. If you remember Charlie's figure, we have a gauge at Bellport, and we have a gauge at Smith Point, which is just slightly to the east and to the south. So it's one location. I'm sorry, I don't have that figure. Let's see. Smith Point. Smith Point is right. Smith Point is right. Sorry. Smith Point is right there. Okay. So it's right here. So we have a gauge there.
So we don't know how the breach spatially might have impacted the surge.
No, it deserves analyzing the surge response From the other gauges at Belfort, Blue Point, Islip, and Tanner Park. So that should be done, and we should be looking at longer records.
Could be done also numerically.
Excuse me?
You can do it numerically too.
You can do it numerically, but the point I was trying to emphasize, I think we should look at some of these observations in concert with the numerical simulations. So these are observation data. So there is some increase in surge response. Malcolm, you look quizzical.
Well, if I understand the physics here, you say in the short term, 2 or 3 hours, wind blowing onshore sets up maximum surge at this point or Belfort. Where does that water come from?
Well, if you blow this way,
Yes.
at short, fast, high-frequency storms, you'll get offshore transport downwind. You only get a longshore Ekman response for an inertial period.
I know, so look at the short term, 2 or 3 hours.
Short-term,
Where
short
does
period
the water
fluctuation.
come from to set up sea level?
I didn't say it set it up. It was blue. You blow this way, everything drops. So
Where does the water go?
it goes out here.
In that short time period. That's pretty impressive.
Yep. I don't want to Go ahead.
I had a different question. And that is, so you estimated the residence time in Belfort Bay to be reduced from 25 days
10.
and that difference is going to be less and further away. Yeah.
Different compartments as you go further west.
Is there a way to know, like within Belfort Bay, so that back corner, for example, what's happening there, and also as you go further west, how far away before you don't see any change?
I should have brought the picture from the high-resolution simulation, but Belfort Bay was the area where the students conducted the salt balance. This part of Belfort Bay right here actually has relatively short residence time because it's exchanging through here. This has longer residence time, and as you go up here, this residence time in this area is quite long.
Not having been affected by the breach or not?
The effect of the breach was less, and the effect of the breach attenuates as you go to the west.
But any estimate, like how far west before you don't see anything?
Well, when they went to Islip, they saw only a very small reduction in residence time, like 10%.
Okay.
Belfort Bay was like 50% or more than that. So, significant decrease in residence time, attenuating as you go west, and some evidence of enhanced surge response in the eastern Great South Bay from these ops. But the surge data certainly deserve a lot more attention. And
Asking about the surge data, how do you think that would relate to the size of the event? Would it be a linear relationship, or do you just not know from the information that you have?
well, that old simulation, which had a breach roughly 5 times the cross-sectional area, had a huge surge response, enormous. So it certainly amplifies as the cross-section gets larger. But the other thing, it's not just the cross-section, it's the length, the effective cross-section, and the hydraulic radius, which relates to the wetted perimeter. And for this type of system, that takes care in defining the repletion coefficient. Hydraulic cross-section is a big player, but so is the hydraulic radius, and so is the length. And Charlie was getting at the fact that this very large, very shoal flood delta probably has a big influence on attenuating the response. But the inlets respond in such a way that they tend to damp out high frequency flows, and they're more responsive to low frequency fluctuations that we're talking about here. I didn't answer your question, but the surge response will go up if the cross section goes up.
Right, but I was just wondering if it's just going to go up linearly or if it might be some non-linear.
Maybe G can answer that.
Later.
Maybe later.
Okay, any other questions for Bob? Well, thank you.
Thank you.